So maybe straight away to say I've been very honored to be invited to this meeting, but also a bit scared because I have, as many of you know, kind of worked in this field for a long time, but then shifted. And I've been working for the last 10 years more on uncertainty quantification and Monte Carlo methods. And this has been sort of on the back burner. But I have an interest still in this topic, and I was picking a particular topic to tell you about. So it's not exactly what I've promised in the abstract and the title, because some of the stuff I've promised is not yet where it should be. But what I want to focus on is, we've heard already today several talks, and in particular one talk on preconditioners or coarse spaces that are based on solving eigenproblems locally. And there is several communities that are exploring this topic at the moment. And this talk is trying to bring this together. So there's communities in optimization, in approximation, finite element approximation, in model order reduction, and as you know, in domain decomposition, that are all tackling the same question. And the overarching type of discretization or coarse space I'm talking about can be classified as a generalized finite element. So this work is joint work with two of the organizers, Victorita Dolian and Nicole Spilan, and several other people. In particular, I want to focus your attention, Daniel, where I've done most of my work on the approximation side, or all my work on the approximation side, and Panayot Vasilevsky and Ludmil Sikatanov, who were my co-workers on the main theoretical tool I want to tell you about today. So I'll start with some problem formulation and motivation, and then I'll come to the question of if I want to precondition a system robustly, then we know in this community I need to have, on a large mesh, an elliptic problem, I need typically a two-level, multi-level preconditioning approach. And so in the context of subspace correction, which is the framework that encompasses multigrid as well as domain decomposition, the question is, how do I build the coarse space? And the other side of the coin is, how do I discretize in a multi-scale fashion? And the key message I wanted to get across today is that if we work in weighted norms, that I'll get to, then we can get contrast independence of our results. And I will tell you, I want to tell you about three theoretical tools that I find very important in this context, and three practical knobs how to tune our methods in order to make the method more efficient or more robust. But the bracket around 3 is because I will only really have time to tell you about the first one and not about the other two, but I'll mention a little bit. And then the second part of the talk is what I originally had promised, is to tell you a bit about implementing the GenEO, which is a particular type of this coarse space, the GenEO preconditioner in a high-performance fashion, and to apply it to a challenging industry problem in anisotropic linear elasticity. Okay, so here is the model problem for getting the scene set and to describe to you the problem. I'm thinking in the simplest setting of an elliptic scalar equation, which is simply the diffusion equation, where the complication comes not from the PDE being complicated or the domain being complicated, but the coefficient alpha varying on many scales in a non-periodic or ergodic fashion and with high contrast. So that, I mean, very large values, very small values can be very close, jumping coefficients, etc. And these issues that I'm going to mention here are also apparent and will be even more pronounced in other equations, such as elasticity equations. So for simplicity, you don't have to think of a tensor here, although the tensor case can be analyzed as well. But just think of a scalar coefficient which varies over many orders of magnitude. we would discretize. Typically, there's many ways of doing this, but if you think in the variational setting, in a finite element setting, then you'd phrase this problem actually as in its weak form, with a bilinear form here, and a linear form, and you discretize, for example, in a piecewise linear space with a mesh size h. Now there can be two possible aims to deal with this, to solve this problem. I can choose h very small and resolve the coefficients with the mesh, but then I'll have a problem on a very fine mesh and therefore a lot of degrees of freedom, and it'll be costly to solve the linear system that arises. And my question is then how to get which is what's more the topic of this conference, I guess, how to get a robust solver, parallel solver that is robust with respect to strong variations in the coefficient. Or I could ask myself the question, if I'm purely after getting a robust, so a good qualitative answer, but I'm not necessarily needing very fine accuracy in terms of mesh accuracy, then I can be content with not resolving the coefficient, but still wanting to have the correct qualitative features of the solution on this coarser mesh. So the capital H stands for a coarser mesh. But in that case, simple piecewise linears will not be sufficient. It will not be robust, and so we need to talk about how to choose this space. It won't be just piecewise linears. But in both cases, here to get an H-optimal solver and here to get a robust coarse space, the same question arises, namely how to pick the coarse solve, or the coarse space. So there is other examples where this comes up if you study elasticity in bones, or what my project, which I'm mentioning at the end, is about carbon fiber composites, so anisotropic layered materials which might have defects, or two-phase flow in oil reservoir simulation. So a few comments. The variation is assumed to be complicated over many scales, so the mesh size which would resolve it would be much, much smaller than the diameter. So complicated or hard to resolve by a geometric coarse mesh, for example, by an adaptive mesh. Then the first goal, as I said, would be to solve robust in terms of mesh size or in terms of problem size. So you want an order n solver in some sense that is also robust with respect to variations in the coefficients. Or in the other case, as I said, this is just restating what I said, you build a special coarse space, an upscaling or a multi-scale coarse space that resolves on a grid where the coefficients are not resolved, and then the approximation properties depend on this variation and the contrast in the coefficient on the subgrid. So this building of this space, we've seen one case already discussed, could be, for example, by solving local eigenproblems. So it's typically inexpensive to set up coarse space, so you don't want to do it lightly. You don't want to do it if it's not necessary. And so in particular, what is one story I have been telling a lot to people in multi-scale finite elements before is if you're only going to solve with that space once, then you might as well do domain decomposition and not throw away all the information about your local solves, because the cost for building this space is of the same order or maybe even more than the solves, the local solves. But then there is many, many cases where these coarse spaces can be reused over and over in a uncertainty quantification setting where you run some Markov chain Monte Carlo. You might use the space from a nearby problem. In optimization, you might have to solve several times. In time-dependent problems, you might be able to use the basis over several time steps. And the difference between those two cases, and this is where my talk comes in, is that the theory of this goal is much better developed than the theory of that goal. And I'm trying to come up with ideas of how to essentially leverage some ideas from here to prove things here. So this is really just to flash over the existing literature. This is not comprehensive, and it's not even meant to tell you a story. It's just saying there is a huge literature on how to do varying coefficients, strongly varying coefficients in the domain decomposition and multigrid theory. First, there was a lot where the coarsest grid has to resolve the coefficients, and then there has been a lot of effort over the last years in extending this to coefficients that are not resolved, and even very late recently also by people that are in the audience. And then the background for this second case is typically, or can often be found in the algebraic multigrid literature already. So the ideas that I'm going to come to are typically related to energy minimization or energy minimizing coarse spaces, and this is essentially at the heart of algebraic multigrid. And so many of the methods that have been developed here have already been studied in algebraic multigrid before. But the theory is more restricted to this. So now on the other side of the story, we've got a whole zoo of multiscale methods, starting from adaptive finite elements, if you want to call them multiscale methods, to generalized finite elements, to multiscale finite elements, etc. And all the way up to generalized multiscale finite elements, where the local space, so generalized finite elements are just partition of unity spaces, where you can stick in whatever you want as your local space. What I call the locally spectral ones is if you solve a local eigenproblem. Now let's think about where the theory of strong contrast variation goes in this field. So most of the theory, especially up here, is for periodic coefficients and things like that, or highly varying coefficients, small contrast. So what do we know? So there is you can use homogenization theory to show the periodic case. You can exploit scale separation to go beyond the periodic to some quasi-periodic settings. You can do special tricks via using simple inclusions and interfaces. Ivan did some work there, or special flux norms. And then there is a lot of effort recently gone into, and a lot of good work in the case of low contrast, which I'll address later. So there's the local orthogonal decomposition method, there's the works by Babushka and Lipton, and the Gamblets by Ovadi, etc. Now what I want to use is links to the DD theory and a particular result that we have proved with Ludmil, Zikatanov, and Panayot Vasilevsky. As some weighted Bramble Hilbert lemma, as we call it. So I want to show you how these things are related and how we can possibly leverage some ideas from here to prove contrast robust theory for multiscale spaces, and there are some limited results. I'll present some limited results, so I don't have a general theory yet. So this is the basic message, or the basic entry point for the theory, is the classical theory. If you look at the domain decomposition or subspace correction literature, has been to work in H1 norms and H1/2 norms to base your theory on standard Poincare inequalities, and then there is a bit of effort gone into using weighted L2 projections. That's the case where the coarse space resolves, the coarse mesh resolves the coefficient variation. Then more recently, and this is what all these papers that are not, or many of these papers that are not needing the coefficient to be resolved, revolve around, have been to work directly in the energy norm. So instead of the H1 semi-norm, we work directly in the energy norm. And then we need to work, as we will see in a minute, also with the weighted L2 norm. And the first results in this direction are in using weighted Poincare type inequalities, as in these papers. And then in this paper that I'm going to highlight today, we looked at how can we extend that to so typically a Poincare inequality is an inequality where you have control over one functional of your solution over a region, for example, the average or the value at the boundary. And you say, what can I tell you about the energy of the function given that one constraint where I can nail it down? And this one is essentially extending that to the case where you have not one, but multiple functionals. What can I say then? Typically in the Bramble Hilbert setting, you can then control higher order norms if you constrain more than one functional. So there's a sort of a spectral aspect to this. Okay, so very quick, very quick intro to subspace correction and additive Schwartz. So if we're back in our model situation of the diffusion equation with this constant alpha here, coefficient alpha here, not constant, we are discretizing that. Think simply piecewise linear finite elements on a triangular mesh or a simplicial mesh in 3D. And I want to precondition this problem. The subspace correction method says pick a set of subspaces, V0 to VL, and then iterate in those subspaces in an additive or successive multiplicative fashion, and basically do a correction in that subspace. Then under certain properties on these spaces, on the functions in these spaces, you can prove certain results. So in the two-level overlapping Schwartz setting, you would have the first level. The one level would be you pick overlapping subdomains as depicted here, and your subspaces V1 to VL would just be the functions restricted to those subdomains with Dirichlet boundary conditions at the boundary. So that would be your V1 to VL, if there's L subdomains. And then you add, and this is a very abstract way of describing this problem, you add, for the moment, just think of an abstract coarse space that's just the span of a bunch of functions. Typically localized functions, so that the matrix defined on V0 is also a sparse matrix, and we can use our normal technology to solve. But this would be a set of subspaces that defines a subspace correction method in the setting of overlapping Schwartz. And if you simply additively correct in those subspaces, these projections here, applying the matrix A, then restricting to the subdomain, solving on the subdomain extending, then this is a projection, and the sum of those projections gives you the preconditioned matrix M inverse A, where the M inverse, or the M, is called the additive Schwartz preconditioner. And if there is if this sum starts at 0, then you would call it an additive two-level additive Schwartz, because it has a coarse space that couples all degrees of freedom. But this is really in a very abstract way. And then for the rest of the talk, I will always assume that the overlap is generous, so that I have of the order of, say, half of the domain or a third of the domain overlap, at least. You can phrase the geometric multigrid or BPX or other multigrid type methods or preconditioners also in this framework. You'd have to, the VLs now have a different notion. They are subspaces on nested set of triangulations, and then the way you're solving is typically not exact solve, but just a smoother on those spaces. I'm not going to talk much about that. But the important bit, coming back to my theory entry point, is that in order to analyze it, I'm not going to analyze it in the classical H1 semi-norm and L2 norm, but I'm going to work in the energy norm, denoted by this symbol here, and the weighted L2 norm, simply weighted by the coefficient itself. So alpha v squared, so that means regions where the coefficient is high get weighted higher than regions where the coefficient is low.
But it's non-zero everywhere.
It's non-zero. We are in a diffusion. It's a diffusion equation, so already to have a well-posed problem.
Have local singularities.
I'm only considering the case of a fully elliptic, uniformly elliptic problem, and I haven't actually thought about it. It might be possible to think about that. The point to state here for this first part of the results from this paper is that. And it's quite interesting because you can go all the way back to, and I spoke after Harry Iserentan's talk in Oberwolfach, which these slides are from, and exactly the same statement was in his talk. So the classical subspace correction literature, 1990, whatever he wrote his survey, Acta Numerica paper, has the same statement. Just not in the energy norm and the weighted L2 norm, but in standard H1 semi-norm and L2 norm. If there is an operator, pi, an interpolation or quasi-interpolation operator from the finite element space to the coarse space that has these two properties, stability in the norm in the higher order space, in the H1 space, and approximation property with respect to the norm that I'm using in the L2 setting. This would typically then have a domain size in there, this constant. Then you can bound the condition number independently of alpha, L, and H. Okay? And similar result can be found, and is also in here, for geometric multigrid, that just you need a different norm here, a smoother norm, induced by the smoother. But the crucial point for this talk is how do we choose V0, and how do we choose pi, and how do we prove 1? So this is only a statement. If this holds, then the condition number is fine. So how do we choose this, and how do we prove this? So in the first setting, let me just this is a second paper. We wrote 2 papers at the time. In this first setting, let's just assume how far can we push piecewise linears? How far can we push a piecewise linear coarse space on a shape regular grid, but not assuming that the coefficient is resolved? And then the answer is the following. If on every patch omega k, so this is there some? So this is the setting where you have a triangle and then all the triangles that touch. So essentially extended by one layer. Extended by one layer of elements, if on that patch you can actually reduce that to about half that layer as well. But for simplicity, just have the whole layer. And if I'm assuming that this following weighted Poincare inequality holds on that patch, so in weighted L2 norm, I have this Poincare inequality with constant CKP. Then the result here can be proved, and the constants are such that essentially they're proportional to the maximum of these Poincare constants from here, over all elements of the coarse mesh. Okay, and the projection operator would then be just the quasi-interpolation operator, the weighted quasi-interpolation operator, with these weights for each of the nodes of our finite element, coarse finite element grid. So this is standard piecewise linears. Now, what does this mean? When is this bounded independent of the coefficient? This is a whole story of its own. You can look at this weighted Poincare inequality and relate the existence of such a constant that's independent of contrast to local quasi-monotonicity, which we've done in this paper and used in particular for Feti, for analyzing Feti. But it's also the same holds true for Schwartz, and you can have exponentially growing coefficients in one direction, even towards a line or towards a point. You only get some geometric dependence on how small that region is where the coefficient is large, but no contrast comes in there anymore. The coefficient contrast doesn't come in. You can even have these, in finite dimensional settings, you can even have these cross points, and you can have these complicated situations here. But what you cannot have, and this is exactly the crucial thing about weighted Poincare, you cannot have high coefficient, low coefficient, high coefficient. As soon as 2 high coefficient regions are separated by a low coefficient region, you will get, you can actually prove that the contrast is a lower bound for the constant. Okay, so here is just a numerical experiment actually with multigrid in this case. So I'm using geometric multigrid. So the coarse spaces are just coarser finite element spaces. And I'm doing a very simple test where I'm putting 2 islands with high coefficient. And in one setting on the left, the islands are further apart. And in the other setting, they're closer together. So it's the exact same setup for both of them. But here the islands are closer together. Here they're further apart. And you see that when they're further apart, although they're not resolved by the coarse mesh, it doesn't affect the condition number at all, or any of the eigenvalues and the conversions. But in the other case, the smallest eigenvalue does grow exactly proportional to the contrast, okay, or inverse proportionally to the contrast. And then the number of iterations does as well. I mean, this can be fixed, and this community here knows this very well because there's only as many bad eigenvalues as there's islands. But this is just to prove the point that the weighted Poincare inequality constant, the constant in the weighted Poincare inequality comes directly into the bounds. So basically what you do and what we advocate in that paper where we're using these standard piecewise linear finite elements is you can just make your coarsening adapt to a coefficient. Where there is two high permeability regions, high diffusion coefficient regions close to each other, you just keep the coarse mesh fine.
What does quasi-monotone mean?
So quasi-monotone, thanks, I should have really said this. This is the example I usually use as my example. Quasi-monotone means if from every point in the domain, you can reach the point with highest coefficient. So the numbers here mean 1 is the lowest. It could be exponential in this constant here. This is the lowest coefficient, and this is the highest coefficient. And I have to be able, from every region in the domain, to reach the region where the coefficient is highest, only increasing the coefficient. So this region 3 here, if I went straight across, I would have to go through 1. So I'm not monotone. If I went through there, I would have to go through 2, so I'm not monotone. But if I go around the corner here, then I am monotone. That's what I mean. Quasi-monotone geometrically can be a complicated path, but it has to be some path. And if you have to go through a vertex, like in this example, then you get some dependency on the mesh, like something like this, eta over h. In fact, in 2D, you just get log eta over h coming in. So this is the simplest case. But if this is difficult, if you, for example, many multiscale people, they don't want to tinker with the mesh. They just want to slap a uniform mesh over, and then they want to build their core space and hope that it's robust. Well, not hope, and build it so that it's robust. Then this piecewise linears will not be sufficient, and you need coefficient-dependent core spaces. And I would argue that essentially all efforts, or most efforts, at building these coefficient-dependent core spaces are all using the same guiding principle, and that's energy minimization. So it's inherent in when we do spectral decomposition, when we do Fourier discretization, Fourier modes, you use the lowest energy modes and you truncate at some point. And this is just doing the same thing in a fully automatic way for an abstract variational problem. So what I'm stating it as is the following setting. I'm assuming, and you can see that I'm coming from domain decomposition, so I'm assuming I have a bunch of subdomains, or you can think of them as supports. And these supports or subdomains have associated with them a partition of unity, KL. For the simplicity, just think of this as being one of our, I'll draw it again so that it's clearer. So the simplest case would be you have simply a finite element, hat function, and this would be the support. So this would be the support of the jth finite element function, and obviously these supports overlap. They're the supports of all the finite element hat functions. They satisfy all these properties. So they're bounded, their gradient is bounded by 1 over the mesh size, and that's how I'm now building my generalized finite elements. So this is a partition of unity, and now I'm using the following principle to build it. I'm using locally on such a subdomain. I'm now fixing not just one functional, but ML functionals. So I'm prescribing ML functionals that are linear functionals on the finite element space on that subdomain, and I'm energy minimizing subject to those ML constraints. And obviously, in order to build a basis, one way to do this is I set one to be 1, the others to be 0, and then I build m such functions, and that would be these psi LJs. And now together, these two give me a way of specifying a generalized finite element space. I'm simply multiplying the partition of unity times these functions that are local on these supports. I'm projecting them back into my finite element space. and that would be the span of those would be the coarse space.
And why do you need to local bias orthogonality? Is that essential, or?
You mean why?
There's number 2 there, the last condition.
This one?
Yeah.
I don't need it. No, that's one way of building that coarse basis. I don't think I need it. No. Now, I should say straight away, because I will be fairly wide-ranging afterwards, that some methods, in particular the local orthogonal decomposition method by Petersheim, gets around having to multiply with the partition of unity and glue it together, because it builds the basis already in a way that they're conforming finite elements in the space. But my argument is that seen in the right light, they all basically fall into this kind of general framework. In some cases, you just don't see this multiplication, maybe. But let's just not complicate things too much. What I'm saying is, instead of having piecewise linears, I'm generalizing the notion of finite elements, or people have, Babushka and Melenk and so on, to say, give me m functions on the local support, multiply it by a partition of unity, and take that as your ansatz space, then that is a generalized finite element space. Okay, now this importance of energy minimization, I've already said, is already long seen as a guiding principle implicitly in all AMG methods, and explicitly by explicitly energy minimizing in those papers. But now we can do the same statement that I had before as my abstract result, because I can now say that if the quasi-interpolant into that basis of energy minimizing functions, where the constant is simply, the coefficient is simply the functional of V evaluated times this basis function. If this is my quasi-interpolant, then I can prove this. This is what I'll show you under certain conditions on the functionals and on the norms, etc. Then I get that the condition number is actually independent of all constants h and the coefficient in particular. And this would be the global. So this is the local interpolant, and this is the global one, just multiplying with partition of unity. And the assumptions of this theorem, these two, follow from a novel abstract approximation result, which we have coined to be called a Bramble Hilbert, abstract Bramble Hilbert lemma. And so here is this abstract Bramble Hilbert lemma. So you have a Gelfand triple. I don't like these sort of high-flying terms, but you've got a Hilbert space, and then you've got your smoother Hilbert space, or scales, subleft scales you can call it as well. You've got V as your H1 space. Think of V as H1 and H as L2. And then on the other side of this Gelfand triple, you have V primed. So I've got this Gelfand triple with a norm for this Hilbert space H, which can be, for the moment, abstract. I have an abstract symmetric continuous bilinear form, A, and these M functionals in V primed, in the dual of V. And for all V, I'm building my basis via energy minimization subject to these constraints of these functionals. Then I make the following assumptions. So I need A to be positive semi-definite. We had this in the talk this morning. It defines a semi-norm on V, and I use as the norm on V just the sum of the norm on H plus this semi-norm. And I need linear independence of the functionals that I've specified. So given any Q in Rm, I need to find the VQ in V such that this can be satisfied. And then I assume that the norm in the H norm of this V can be bounded from above by the norm of Q with this constant. And then the important bit, which is the one that really relates it to why we call it a Bramble Hilbert lemma, if we can bound the weaker norm by the stronger norm plus something related to the functionals with constants CA and CF. So remember the constants, we have CQ here, CA in front of the semi-norm and CF in front of the functionals. Then the result states that the weak approximation is independent, both of the conditions are independent of CF and CQ. So the important bit is this CF can be as nasty as you wish. It can basically be almost infinity. It will obviously, with rounding errors, that might be a problem. But what I'm trying to say is the important bit is if you can find functionals such that this condition holds, then you're in business. Then the weak approximation property here only depends on the coefficient in front of the seminorm. It's a projection, so this is holds with constant 1. And the constant CQ and CF have disappeared. The proof is actually really straightforward. As I say, it's a projection, so the first assumption holds automatically. From A3, using the fact that when I subtract the interpolant, then all functionals are actually 0. So the second term here just vanishes. And I'm just assuming that's how the CF vanishes. And then you just need to do an upper bound, which I'm doing crudely here. I've added a factor 4 here because I did it not very sharp. But you can get rid of the factor 4 as well. Now, how can I use this abstract result for our problem? And remember, I've already advocated this weighted L2 norm as our norm in L2. So I'm using that. I'm gonna have to come up with functionals, and that's gonna be my knob 1. Remember at the very beginning I told you I'll have one knob that I can fiddle around with. That's the choice of the functionals. So for many functionals you can build them in such a way that they are linearly independent. And then the important bit is, can I verify assumption A3, because then I'm in business. For one functional, this reduces to the weighted Poincare inequality and to quasi-monotonicity. For more than one functionals, it now leaves open the possibility to get robustness even with non-quasi-monotone coefficients. But the nice thing is this is completely abstract. And so this is for this setting, but I can use that for other settings as well. So here is some functionals. So the first one was Galvis Effendiev. They solved eigenproblems, local eigenproblems on each sub-region here, which are having the stiffness matrix on one side and the mass matrix on the other side. If you do that, then that actually is equivalent to solving an energy minimizing problem with the functional being the integration of the function against the first m eigenfunctions. So obviously you wouldn't solve it like an energy minimizing problem, you would solve the eigenproblem, but it's equivalent to using as functionals the integration against the first few eigenfunctions.
But that requires that your alpha is not too much varying in this local domain, right?
No.
If you would here have a highly varying alpha,
then you just get a lot of eigenfunctions. So
then you have to increase the number of eigenfunctions.
Yeah, so that's right. But that's why we're coming at the very end to this GenEO space where we're trying to restrict to the overlaps and to different right-hand sides. The one that was the main example in our paper where we advocated this Bramble Hilbert lemma is you just say, if I don't have weighted Poincare on the whole domain, let's just split it up however we want so that it holds on parts of the domain, and then we do something like wavelets. So one basis function is average 1 on one region and average 0 on the other, and the other one is the other side. So you solve these saddle point problems in order to find eigenfunctions, basis functions. Then in this paper with Nicole and Victorita, we used the Dirichlet-to-Neumann operator on the boundary. So we solved an eigenproblem with the Dirichlet-to-Neumann operator that avoids the problem that, but still has a problem obviously if there is variation across the interface. And then in the paper, in the GenEO paper that was already mentioned, we took a completely different kind of right-hand side functional, which is this GenEO type eigenproblem. But the one thing that I specifically said to the audience in Oberwolfach, which was mostly multiscale people, is that the Bubushka-Lipton paper, which is a paper about approximation theory, an abstract approximation theory paper about generalized finite elements, has also got a functional, which is just an eigenproblem where one region. So the eigenproblem there is Neumann matrix on a big domain, Neumann matrix on a small domain. Solve the eigenproblem for that. Then that gives you the first m eigenfunctions would form the coarse space, or would form the approximation space. LOD you can think of, so you for those who know LOD, you first take piecewise linears, you subtract, you look in the kernel of the quasi-interpolant on the piecewise linears, and then you orthogonalize. That basically means you're constricting the average over one patch to be 1, and over all other patches to be 0. So it falls in the same game, and Ovadis gamblets as well. Now, just to show you that this crucial assumption A3 can be proved, I show it to you for these first two. So for the second one, which is the case where we're assuming that on our domain I have weighted Poincare inequality here and weighted Poincare inequality here, then I can simply split my integral over the two regions. I get that the part coming from the functionals does depend on the contrast in the coefficient, but for the other part, I can use weighted Poincare here, and I can prove that that because I know weighted Poincare holds here and holds here, that this constant here is benign, and so this constant CA is benign, and I get essentially that the constant that comes out is the maximum of the weighted Poincare inequalities, but now over subregions. In the case of the eigenproblem with the mass matrix on the right-hand side, you essentially, by design, you've eliminated out all the eigenfunctions corresponding to the first few eigenvalues. So the remaining one, the first one that plays a role, is the m plus first eigen, or 1 over the m plus first eigenvalue. So then the constant is just that. And then this is the link to reduced order modeling. There is a whole host of papers by Patera, Boer, Smetana, etc., where people are now building localized reduced spaces methods, and they are all using the same technology as well. But in addition, this particular paper is very interesting because they use randomized eigensolvers, which is something that I advocate as well, instead of using RPAC or direct eigensolvers. So how can we use this to obtain a contrast-robust approximation theory? And I'm looking on the clock, okay. I'm still all right. So this is now to show you how the technology from domain decomposition can be shifted and lifted to prove something about these multiscale methods. And I'm going to do that in the context of the local orthogonal decomposition method, localizable, I think it's called actually, sorry. Localizable orthogonal decomposition method by Malmquist and Petersheim. So you start, in that case, you can think of this again as your partition of unity that I spoke. So you start with the standard hat functions as your initial coarse space. You define a quasi-interpolation operator where you basically average around each hat function, and that would be your quasi-interpolation operator into the coarse space. Then you look at the decomposition of all of the full finite element space into this span of these guys plus the detail space, and the detail space lives in the kernel of this quasi-interpolation operator. And then what you do is now you look at the projection operator, the fine-scale projection operator that essentially maps any element v in VH into this kernel of pi by orthogonal projection here. But this is a global problem. And now the direct sum of the space that would be 1 minus this orthogonal projection applied to VH and VH fine is orthogonal. So these two spaces are orthogonal. And this VH multiscale is in some sense an improved coarse space over this one. But we are solving a global problem, and in fact the way you do it is you take a hat function over one region, and you solve this global problem, the support of the hat function will grow. It will have influence outside, but as you see already here, the change from the original hat function to this multi-scale hat basis function is very small, and it's very localized. And in fact, you can prove, and this is tool 2 that I'll mention in a minute, you can prove that the influence or this size of this correction decays exponentially fast as you move away from the support of the original hat function. And this is what's exploited because the exponential decay of the energy of this function basically means that the energy over the region excluding from omega the interior, the dark gray bit, is exponentially small in comparison to the energy of the whole function, and with some gamma less than 1. And you can basically then aorthogonalize or write an approximate aorthogonalization problem, a localizable one, that only works on this omega jk patch. So you extend your patch by 1 layer, 2 layers, 3 layers, for example, and solve your orthogonalization problem only on that patch. So in the context of my big theory, this would now be my support of the final problem. And obviously many functions have, many of these little patches have overlap with this. So this would be the functionals that we're constraining in our case, because we are looking only in the kernel of this quasi-interpolation operator. Okay, and then this localized multi-scale finite element space solving this approximate aorthogonalization problem is then defined to be the LOD space. And what you then solve in the end is you solve only a problem in the coarse space. So now we're back at my very initial aim. Instead of solving the fine scale problem with the domain decomposition solver, we've built now a good coarse space, and we're only solving this. And we are content with finding this multi-scale approximation to our problem. But there is an approximation result that says that this converges with rate h plus something that goes like gamma to the k. So this is the usual approximation error part, and this is this localization error. Now, if I pick the k such that this whole k to the d, gamma to the k, is of order capital H, then the whole error bound is of order capital H. So this is the game they play, and in fact, you see very quickly that the k, the number of layers you have to overlap, grows only logarithmically in 1 on h, but with base gamma, and I'll come to that. So the gamma is this thing at which exponential rate you decay. Now the problem is that unfortunately this gamma goes to 1 as the contrast goes to infinity. So in particular in channels where the coefficient is large, you will see very long influence of the hat function. As you can imagine, if you have a channel where the pressure is, you all have done this model problem. So this is essentially where the pressure is constant along that channel. Then your basis function has to essentially go very far in order to see that. So, and secondly, the hidden constant also depends on the contrast. So in 2 places you're lost. First of all, the localization is not a local problem. It's quite global or quite large. And secondly, the constant depends on this. So how can we do a high contrast theory? And the answer is, again, and I'm only focusing on this here, the answer is again looking at these 2 properties. Stability in the energy norm and weak approximation in the weighted L2 norm. If we have those 2 properties, here phrased as one assumption, then we can do a similar proof to the original LOD, and this is my work with Daniel Petersheim, where now the constant gamma in the exponential in the exponential term is e to the minus 1. And so, but there is this term here which depends on the contrast, but that's algebraic, and this is exponential. And so I only need logarithmic growth in the contrast and not linear growth in the contrast anymore. And the second thing, well, the rest is all under control. But the problem is that in order to prove this, we're using weighted Poincare inequality again. And so we're only allowed to go a little bit beyond resolving coefficients. And the way we do it is so the reason you will see why there's an error here, this should be th, t eta, and this should be t little h. So if we assume the coefficient is piecewise constant on some grid between t capital H and t little h, and we use this weighted quasi-interpolation operator, then essentially by the weighted Poincare inequality, we can prove that this condition, this crucial condition holds, but the constant depends on h over eta. And so if we have very highly oscillatory things, which is what you had in mind, I think, then this will not work. This will only work in a certain regime beyond the standard thing. And also the other constant goes even quadratic in h over eta. The crucial, so in summary, we do get contrast-independent convergence rate, but under stringent assumptions on the type of coefficient variation. And the key tool in proving this, and this is the tool number 2 that I wanted to highlight, is a weighted Cacciopoli inequality. So one thing that I've already said to many people, including Nicole, that I think I found very interesting from the theory in multiscale finite elements, or in generalized finite elements, is that once you, or in LOD, if your energy minimization problem with functional constraints is such that the functionals have support on a smaller region than where you're solving the eigenproblem. So you're solving the eigenproblem on an extended region, and the functionals are supported on a smaller region, then you can use this Cacciopoli inequality. This Cacciopoli inequality is basically saying that any aharmonic function on the bigger domain, you can control the energy on the smaller domain by the weighted L2 on the bigger domain, and the constant is 1 over the distance between the two. And that's where you can play this exponential game again that I showed before. So this is the second tool that I advocate for analyzing the problem. And that's where the story ends, because I haven't really got any more results. So I've already told you either I can adapt the grid to make it robust, I can enrich the local space, or change the functionals. But in order to prove this rigorously, for LOD, I believe it just reduces to refining the base grid, TH, which people will not maybe be prepared to do. Then I can prove it. In generalized finite elements, and this is where we're working at the moment, is how can we combine the two tools I've showed you and prove something contrast robust. And the last 5 minutes I have, I will just show you one, and give you a third tool, and in particular advocate the functional that we are the most keen on. So in my energy minimizing space with functionals, which is the GenEO coarse space, and I'll advocate it on the basis of this problem, which I have 2 collaborations on. So if you're interested in the simplest case in the linear, we are also in the long run interested in nonlinear elasticity, but even in the linear elasticity case. So again, I have a very simple elliptic differential equation, but the complication comes from the C, the tensor here being highly varying and strongly anisotropic. In this case, strongly anisotropic. So the one extra bit I've added now is that I'm interested in particular in anisotropic coefficients, because these carbon fiber composites, they have particular direction which they're anisotropically varying. So this is a 5-year project with several universities in the UK and with GKN and other suppliers for Airbus and Boeing to certify or to build a better way of designing and certifying aerospace composites. And this is a project with the Turing Institute and some company in Holland, where they're 3D printing a bridge. And this is basically sintered steel. This is steel where you put a powder and then run a laser over it. So the structure of the steel here is highly stochastic, and you need to do uncertainty quantification. So both of those are multi-scale simulation projects, so needing good solvers or discretization techniques embedded in what's my current bread and butter in an uncertainty quantification setting. And the one thing why I'm picking this is to show you what's the advantage of the GenEO setting. And there is one tool I want to show, and this is, so essentially one thing that I have completely left under the carpet up to now, which is at the heart of all these Schwartz theories, subspace correction theories, is that in order to prove this result that I showed already several times, that the condition number is bounded independent of the constants if we have this, these two assumptions, is the stable splitting. So for any function v in my finite element space, I need to be able to find functions in the subspaces, in my subspace correction setting, such that v can be written as the sum of the VL, and that the energy of the sum of the energies is bounded by the energy of the original function v with a constant c0 squared. Now one observation, which is I think the key observation in the GenEO paper, is that this assumption is something that can be localized and can be requested of your space locally by having subspaces VL, capital VL, that satisfy this property. And this is where then the eigenproblem comes from. If you choose your subspace in such a way that the first few eigenmodes are suppressed, are indexed in subspace. So if I subtract the coarse correction, okay, I should show it here. So if you subtract an element of the coarse space and then restrict to your subdomain, then this function will not have any contribution from the coarsest eigenmodes anymore on that subdomain, and therefore this constant will only depend on the m plus first eigenfunction, or 1 over the m plus first eigenfunction. And then, because of this lemma, which is the crucial tool from this paper, this automatically gives us the global stable splitting property, where the constant C0 up here depends on the constant C1 down here in this way. This is not the optimal constant, but it's robust with respect to coefficients. And this motivates to solve the following eigenproblem, where the partition of unity here plays a role. And the reason why I think this is an interesting thing also to pursue in the multi-scale setting is, if you think back at what I told you about the Babushka-Lipton generalized finite elements, they solve an eigenproblem for the big Neumann matrix versus the small Neumann matrix. This is purely saying I'm solving an eigenproblem for the big Neumann matrix, and then this is just partition of unity applied. So this is the Babushka-Lipton is a special case of this. With discontinuous partition of unity. Okay, so we've implemented this in DUNE, in our package for solving carbon fiber composites. Here is a simple cantilever beam with 12 layers. It's a flat plate under uniform pressure on the top surface, fixed on one side. The layering is such that the fibers are in 90, 0, minus 45, plus 45 in this order. We're using 20-node serendipity elements. It's a quadratic element, but not quite the full quadratic element, which avoids shear locking. And then you see that under load it bends down. Here is a set of eigenmodes that we get. You see that the convergence with GenEO is fully robust versus the no coarse space case. And the zero energy mode in this case actually does a good job as well. But the GenEO is fully robust and needs very few iterations. The Boomer AMG, for example, for this problem, in the setting that we took it from, you can probably tune it, or maybe you can tune it. We haven't managed to tune it. Does not converge robustly for this problem.
What are the
The
timings?
timings are. We didn't. This is slower than ours with these iterations, but it's not like the per iteration. This is cheap. I have a paper on a line here, so I'll come to the cost for hours. We haven't really put a full comparison of the Boom AMG on the big problem because these iterations just explode. It just doesn't work for the big problem. So the big problem is a full wing box or an artificial setting of a wing box where the layering changes. So in the corner, the type of angles they use is more towards 45s and minus 45s to avoid the corner opening. And then the top and bottom, the lid has a different layering structure. And so there is a transition zone where it changes orientation, the fibers. And we also have a defect in one of the corners, which you can't see because it's so small. But there's a little defect, a small defect in one corner. And this is then the implementation run on the Archer, the HPC cluster in the UK, on up to 16 or 12, 13,000 cores. And you see that the run is fully robust. And now coming into Axel's question, the cost is essentially the setup cost mostly. And so AMG would have a much lower setup cost. And so I mean, if you can tune it to converge, then it's a question of how much faster each individual layer is. But this is a fully robust setting. The most cost is in the setup here. We're going up to 2 times 10 to the 8 degrees of freedom. We're also showing here a strong scaling experiment where we're changing how many degrees of freedom per processor, which in this regime that we've chosen, we know, everybody knows, if I make the number of nodes per processor too small, then this will bottom out at some point. But it seems to really work and get problems that are of real interest in the industry into the feasible range. Okay, that's it. So we want to extend this to nonlinear and to composite failure as well. I always have to rein in the expectations of my collaborators on this. More complicated geometries, bigger overlap, and use the coarse space as I advocated the whole time also as on its own. When we get to really big problems, we don't really want to solve on the fine grid anymore. We just want to work on the coarse grid. And then use that as a surrogate in Bayesian inference problems. I won't talk about the other two knobs. That's basically what partition of unity to choose, which seems to have a big effect. And I've already mentioned that randomized eigensolvers randomized linear algebra seems to be very efficient. And as I said, the theoretical aim is to prove some contrast-independent approximation theory. Thanks. Yeah, if anybody wants to go climbing on Wednesday, I don't know any of the rock climbers in here, so let me know.